great. We've done piecewise functions. We have not done piecewise functions though with sine and cosine. So it's a little bit of a different beast. So if I were plotting this, I'd start with my sine curve, which the parent graph just looks like that, right? And that's as if the entire domain was the sine curve, which it's not. We only want to see this sine curve when x is less than 0. So here's where x is 0. Open or close circle. Open. Now I'm nervous. Nate, why did I make that open? Versus what would have justified me closing it? What would I change if I was supposed to close it? So where do we look to determine open or closed? Like here, sine x. So what would that need to be though if that was going to be a closed circle? Who can help them out? Trista? Right. This is the function we're graphing, but to decide open or closed, we actually look at the interval, right? If we wanted that interval when x actually equaled 0, we would fill it in. But we only want it when it's less than 0, so we keep it open, okay? Now, the next function is a cosine curve that has been flipped upside down and shifted up 1, right? Can we all agree that that's the same thing as negative cosine of x plus 1? So it's been flipped upside down and shifted up 1. So its midline, I'll say, is at 1, which is where the top of the sine graph is. But it's a negative cosine. So positive cosines go max to max. Negative cosines go min to min. And what's the amplitude of this? What's the amplitude of this negative cosine x plus 1 curve, Mitch? No, the amplitude. So your function format for trig is this right here. Which of those letters is your amplitude? A. So what's your amplitude here? 1. Exactly. So when it comes to like starting at a minimum, it's going to be 1 unit below the midline, which is actually going to pick you up where the sine curve left off, right? And because it's a less than or equal to, with the 0 being less than or equal to x, we'd actually fill that circle. And then your negative cosine curve would look like that. But we only want it from 0 to pi. Now, what is this? What is the length of one period of this? 2 pi. So if that's 2 pi, then I actually need to cut this off way back here at pi. Oops. And x is less than or equal to pi, so since there's an or equal to on that, it's also going to end. This is 0, this is 1, this is 2. It's also going to end with a closed circle up at 2. And then we're just following the regular cosine graph with no flip, with no shift from pi and beyond. So if I'm just drawing the regular cosine graph, it would start at 1 and it would end at 2 pi, and it would just keep going, and you'd get another one in by 4 pi. That's just the regular cosine curve, yes? But we only want to see it when x is greater than pi. So pi is where this minimum is happening. So I'm going to do an open circle there, and I'm going to get rid of that previous part because that's not the interval that they want. So we have to graph 3 trig functions here. And then we have to know how to like erase the parts that we don't need based on the interval provided. So that's a lot just to get that picture on your paper, okay? Sometimes people do piecewise functions by just looking at where the endpoints of each graph are. So like this one ends when x is 0. It's an open circle, I know, but still, where would that point be? And they would plug in 0, and the sign of 0 is 0, so they would know that that graph is ending with an open circle at 0, 0. And they would kind of use that. This one is beginning at 0, which if you plug in 0, cosine of 0 is 1, 1 minus 1 is 0. So this one is beginning at 0, 0 with a closed circle, so it kind of plugged up that open circle that we had had previously. And it's ending at pi with a closed circle. Now, if you plug in pi, cosine of pi is negative 1. 1 minus negative 1 is 2. So there it is ending at pi 2. Now with lines, dealing with the endpoints is easy because then you can just connect them. But we know that these 2 points are not connected with a straight line. It's got to be the curvature of a trig graph. And then lastly, this one is picking up at pi, albeit it'll be an open circle, but still, to figure out where that open circle is, plug in pi. So cosine of pi is negative 1. So x-coordinate pi, y-coordinate negative 1 will be the open circle starting that cosine graph. And that will just then continue forever. So once you have an image of that, identifying the values of c for which the limit as you approach c does not exist. So looking at this, Aiden, where would you say the limit does not exist? When x equals pi, correct. And that's the only time. Now we learned last chapter that sometimes graphing it isn't necessary, right? Whenever you're looking at piecewise, you're concerned with the point of transition. So you're concerned with what the limit is as you approach 0 from the left versus what the limit is as you approach 0 from the right. And then your other point of transition is pi. So you're concerned with what the limit is as you approach pi from the right versus what the limit is as you approach pi from the left. So as you approach 0 from the left, which of these intervals is to the left of 0? Bridget? The first one, right, to the left of 0. So you would, to find that limit, you would plug 0 into this. Sine of 0 is 0. So the limit as you approach 0 from the left is 0 versus the limit as you approach 0 from the right. Morgan, which equation would I use for that? Right, just to the right of 0. So you'd plug 0 into that, and you'd get cosine of 0 is 1, 1 minus 1 is 0, and those are a match. That's why this limit does exist. If you jump to the other point of transition, pi from the left would be equation number 2. That's going to give you cosine of pi negative 1, 1 minus negative 1 is 2, versus pi from the right, cosine of pi is negative 1. And that is not a match, so that does not exist. So I still think this is the more efficient way, certainly. As long as you wrap your head around it and you know what you're doing. Okay? And so that's why we kind of reviewed the graphing technique. Okie doke. Okay. So, by the way, because that limit existed here, because this graph ended and the other one coincidentally began at the same moment, we kind of created continuity there. Yes? As well. All right. We're going to sketch a graph, and there's a few on your homework that have you do this, that contains these features. So right now, go ahead and sketch the first step of this graph such that f of negative 2 equals 0. What would that do for your graph? If f of negative 2 equals 0, How does that show up in the picture? Sarah? Okay, perfect. So whatever our function is, it has to go through that. Okay? Next piece. F of 2 has to equal 0. So Bailey, where would that show up on your graph? 2, 0, good. Now, the limit as I approach negative 2 has to be 0. So here's negative 2. My limit as I approach it has to be 0. Meaning when I come from the left and when I come from the right, it has to, both sides need to be going towards that point, essentially, right? There are 1,000 ways this could look. No, 1,000 might be a stretch. That's a stretch. You could approach it from the left and you could approach it from the right in that fashion. You could approach it from the left and approach it from the right in that fashion. You could approach it from the left this way and approach it from the right that way. Or you could approach it from the left this way and approach it from the right that way. Either one. It's fine. Okay? So let's just stick with the last one I have on my paper. The limit as I approach positive 2, however, should not exist. Again, there's 1,000 ways I can do this. It doesn't, no one said it had to be a continuous function, did they? In fact, it absolutely can't be. Because if your limit doesn't exist at 2, it's definitely not a continuous function. So you could just make it continuous until then, but then do something crazy as you approach 2 from the right, just so the limit doesn't exist there. You could not go towards that point at all. You could just, do something like this and end it with an open circle there. And then you could start it with the closed circle or leave it the way it was, where it's like a total jump and then just a removed point sitting there randomly. So lots of ways that you can get through your features. You have to have a point here and here. That's undeniable. But the way in which you make the limit be 0 here and the way in which you make the limit not exist here can change. We even could sort of make this an asymptote if you really wanted. You could do, it wouldn't be an asymptote because there's a point on it, but you could have it like have an asymptote type behavior. Something like that. So in theory, there's an asymptote there, that there's just a piecewise function that puts a point right there for you. So lots of options. Okie doke. Any questions on that? Okay. Flip to the back. Think about this for a second. All right, so any idea what this graph looks like? Any idea? No, I don't. I don't think I do. No. If it was just an e to the graph, it's that over x that really throws us. So direct evaluation, you think about plugging in a 0. 0 divided by 2 is 0. E to the 0 power is 1 minus 1 is over 0. Indeterminate. Okay. Manipulating. I don't know how to manipulate. Okay. So let's see, graphing. Any idea what the graph looks like? I already talked about that. Probably not, right? This is very similar to what was just on our test, on our quiz, right? This is actually, it's not the same graph, but it's very similar. I think this is the only part that's different. But then plugging in values, and let's just see what we can do without a calculator to see if it's even practical. If I plug in something like 0.0001, I'm approaching 0 from the right. in this case, okay, by plugging in 0.001. That's going to be e to the 0.0001 minus 1 over 0.0001. So that just got even smaller when I did that, right? So if you think about the E graph in and of itself, it looks like this, right? As I plug in X values coming from the right on that, they get closer and closer to 0. And then you're dividing it by 2, so it's getting even closer to 0. This is definitely approaching 1, right? And 1 minus 1 would be 0 over 0.001 is still, so this is never actually going to be 0, but it's going to be teeny tiny. We're really close to 1. Let me think. This is going to be really close to 1, but then when you subtract 1, this is going to be really close to 0. Teeny tiny over teeny tiny. That's still indeterminate. We can't really gather what's going on. Sometimes if the numerator stays a constant and the denominator gets tinier and tinier, that's helpful, because even though we don't know the actual numbers, we can see. But this would still be indeterminate. So there's really no way we can do this except for with an exploration on a graph or on a table. So just to do the graphing, because I think it's quicker. Your numerator would be e to the x over 2 minus 1 divided by x. Zoom 6 will bring me back to. Okay? It doesn't look like it's quite 1 this time, does it? Looks definitely below it to me. So if I zoom in around whatever that might be, now we can see even more clearly that it's definitely not 1. It's actually probably, if you were guessing, what would you think that that is? I would guess probably 0.5. But I wouldn't guess and let that be my final answer. I would want to know for sure. So I would set up my table to start at 0, because that's what I'm approaching. And I would get closer and closer to it by something really small. And then I would look at that table, and I would see coming from the right, it's getting smaller and smaller towards 0.5. And coming from the left, it's getting bigger and bigger towards 0.5. So your answer there is 0.5. I'm pretty sure your book in some sections will say use your calculator. And that way you kind of have a feel. And if you ever want just double clarification, ask that the next day. Like number 37, we would need a calculator for that, right? And then I'll take a look at it and I'll say yes or no, here's how you should know what that looks like. Okie doke? All right. Do you remember these symbols? Remember those? Greatest integer function. So like these symbols, it's been a while, of like 2.1 means what's the greatest integer less than that? Or less than or equal to 2. If I gave you the greatest integer symbols around 2.9, the answer would still be 2. Okay? I'm not going to graph this function by hand. I'm just going to type it into the calculator, because those greatest integer symbols can be found under your math window, kind of near where absolute value would be found. And negative parentheses x minus 1 goes inside. Okay, so zoom 6, this is what that looks like. So I don't know if you can see it, but something popped up there and something popped up there. Yes? I'm going to guess my window's not big enough to show the rest. So I would maybe open my window negative 20 to 20 and see what happens. Okay, there we are. Step, 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 step. We get a little bit more there, right? So if you look at what is the limit as you approach 3.5, you could look at your function value at 3.5. Now, second trace value, 3.5, would be 47.25. So that's actually way off my graph. If I want to zoom in up there, I could change my X max 0 to 4. And then what was it? 40-ish? 47. If I go from 40 to 50, I'll get a better feel. Here's 3 to 4. And 3 point... What did I do, 3 to 4? Oh, I did 0 to 4. Let me do 3 to 4. Oh. So from 3 to the 4, it's the same step the entire time. And it is 3.5. It's not, there's no hole there. You could just plug in 3.5 and you would get that answer of 47.25. On the other hand, right at 3, so let me give you this window from 2 to 4. And I'll do 0 to 50. From 2 to 4, here's 2 to 3, here's 3 to 4. We have a jump right at 3. So what's the limit as you approach 3? Does not exist. Okay? So with jump functions, you have to be careful. If you're at the end point of a step, the limit's not probably going to exist. Okay? There are some true false on your homework. Maybe we'll start by discussing these tomorrow, but you'll have some true false on your homework that you might want to discuss as well. So page 73, that little section there.